始めます。と、Statistical Mechanics。なんか音が鳴ってる。いいのか。Statistical Mechanics。だけど熱力学、サーモダイナミクスを勉強します。で、今日は6ページからなので、6ページが出てこないの。6ページ、ここからです。これ The First Law of Thermodynamics。 ちょっとノイズが多くてすいません。これなんだろうね。ですか。I don't know why we have so much noise here. Anyway, the first law of thermodynamics. In an arbitrary thermodynamic transformation, let delta Q denote the net amount of heat absorbed by the system, and delta W the net amount of work done by the system. The first law of thermodynamics states that the quantity delta U defined by delta U equal delta Q minus delta W is the same for all transformations leading from a given initial state to a given final state. This immediately defines the state function U called internal energy. Its value for any state may be found as follows. Choose an arbitrary fixed state as reference. Choose an arbitrary fixed state as reference. Then the internal energy of any state is delta Q minus delta W in any transformation which leads from the reference state to the state in question. It is defined only up to an arbitrary additive constant. Empirically, U is an extensive quantity. This follows from the saturation property of molecular forces. Namely that the energy of a substance is doubled if its mass is doubled. Saturation property of molecular forces. The experimental foundation of the first law is Joule's demonstration of the equivalence between heat and mechanical energy. The feasibility of converting mechanical work completely into heat. The inclusion of heat as a form of energy leads naturally to the inclusion of heat in the statement of conservation of energy. The first law is precisely such a statement. In an infinitesimal transformation, the first law reduces to the statement that the differential du equals dq minus dw is exact. That is, there exists a function u whose differential is du, or the integral du is independent of the path of the integration and depends only on the limit of integration. This property is obviously not shared by dq or dw. given a differential of the form df equals g ab dA plus h ab dB, the condition that df be exact is partial g partial b equal partial h partial a. Let us explore some of the consequences of the exactness of du. Consider a system whose parameters are pvt. Consider a system whose parameters are pvt. Any pair of these three parameters may be chosen to be the independent variables. Any pair of these three parameters may be chosen to be the independent variable that completely specify the state of the system. The other parameter is then determined by the equation of state. We may, for example, consider u equal u of p, v, then du equal d partial u partial v partial p at constant v, dp partial u partial v at constant p dv. The requirement that du be exact immediately leads to the result partial v partial u partial p at constant v at constant p equal partial p partial u partial v at constant p at constant v. The symbol, now I'm reading the footnote, the symbol partial u partial v at fixed v denotes the partial derivative of u with respect to p with v held constant. The following equations expressing the heat absorbed by a system during infinitesimal reversible transformation, in which dW equal P dV. Infinitesimal reversible. Are easily obtained by successively choosing an independent variables, the pairs B, PV, PT, and VT. DQ partial U partial U partial P constant V partial u partial v with constant p q dq du plus dw. This is dq du plus dw, and this is p dv. Partial u partial t okay, so this is t, this is p, so we have this part comes from like partial u plus pv dt with fixed p, and this part is partial u plus pv partial p with fixed t. Let me see. Is there any systematic way to do this? dq equal, let's see, pdv. This is pdv, then partial u I think this is more like partial u partial p at constant v plus p partial u partial v partial v at constant v. Constant p, sorry, this is constant p, this is partial p. Then because v is held constant, so this is 0, then we can consider this part. This part is partial u. Now we fix p. Let me consider, sorry, partial u partial v at constant p plus p partial v at constant p times dv, and this is 1, so we have this. Okay, then if we consider tp partial u partial t plus p partial b partial t at constant p dt partial u partial p at constant t p times partial b partial p at constant t dp. Okay, then if we choose t and v, we have partial u partial t at constant v. Partial u partial v at constant t plus partial p Okay, so called dq equation. It's called the dq equation. Those are of little practical use in their present form, because the partial derivatives that appear are usually unknown and inaccessible to direct measurement. They will be transformed to more useful form when we come to the second law of thermodynamics. It can be immediately deduced from the dq equation that heat capacity at constant volume Cv is delta Q divided by delta T at constant volume. A partial U so this is like a TV. You can use TV, I think. We can use this equation, then we don't change V, so this is 0. And we have constant pressure heat capacity. Constant pressure heat capacity. So we use the second equation. So Cp is partial U partial T at constant pressure plus P times partial V partial T constant pressure. This is U. This is U. Okay. And this is called enthalpy. We consider the following examples of the application of the first law. Analysis of Joule's free expansion experiment. The experiment in question concerns the free expansion of ideal gas into vacuum. The initial and final situation are illustrated in figure 1.3. Experimental finding T1 equals T2. Deductions W equals 0 since the gas performs no work on its external surrounding. Delta Q equals 0 since delta T equals 0. Therefore, delta U equals 0 by the first law. Water bath, vacuum, gas. Thus, two states with the same temperature but different volume have the same internal energy. Two states with the same temperature but different volume have the same internal energy. Since temperature and volume may be taken to be the independent parameters, and since U is a state function, we conclude that for ideal gas, U is a function of the temperature alone. two states with the same temperature but different volume have the same internal energy. Since the temperature and volume may be taken to be independent parameters, and since U is a state function, we conclude that for ideal gas, U is a function of temperature alone. These conclusions can also be reached theoretically without reference to a specific experiment with the help of the second law of thermodynamics. Anyway, internal energy of ideal gas. Since U depends on T, 1.8 yields Cv equal partial U partial T at constant V equal du dt. Assuming Cv to be independent of temperature, we obtain U equals Cvt plus constant. The additive constant may be arbitrarily set equal to 0. The quantity Cp minus Cv for ideal gas, the enthalpy of ideal gas is a function of T only H, a function of T only H equal U plus PV, which is equal Cv plus Nk times T. Hence, from 1.9, Cp is partial H partial T at constant P, which is dH dt equals Cv plus Nk, or Cp minus Cv is Nk. Thus, it is more efficient to heat an ideal gas by keeping the volume constant than to heat it by keeping the pressure constant. This is intuitively obvious. At constant volume, no work is done, so all the heat energy goes into increasing internal energy. 1.3. The second law of thermodynamics. Statement of the second law. From experience, we know that there are processes that satisfy the law of conservation of energy, yet never occur. There are processes that satisfy the law of conservation of energy, yet never occur. We know that there are processes that satisfy the law of conservation of energy, for example, a piece of stone resting on the floor is never seen to cool itself spontaneously and jump up to the ceiling. Okay. From experience, we know that there are processes that satisfy the law of conservation energy, but never occur. Okay. I think we can change yet to but, then I understand. We know there are processes that satisfy the law of conservation energy, but they never occur. For example, a piece of stone resting on the floor is never seen to cool itself spontaneously and jump up to the ceiling, thereby converting the heat energy given off into potential energy. The purpose of the second law of thermodynamics is to incorporate such experimental facts into thermodynamics. Its experimental foundation is common sense, as the following equivalent statements to the second law will testify. Testify or not testify? What is testify? Testify. Its experimental foundation is common sense, as the following equivalent statements of second law will testify. Kelvin's statement: there exists no thermodynamic transformation whose sole effect is to extract a quantity of heat from a given heat reservoir and to convert it entirely into work. Clausius' statement: there exists no thermodynamic transformation whose sole effect is to extract a quantity of heat from a colder reservoir and to deliver it to a hotter reservoir. In both statements, the key word is so. An example suffices to illustrate the point. If an ideal gas is expanded reversibly and isothermally, work is done by the gas. Since delta U equals 0 in this process, expanded reversibly and isothermally, the work done is equal to the heat absorbed by the gas during the expansion. Hence, a certain quantity of heat is converted entirely into work. This is not the sole effect of the transformation. However, because the gas occupies a larger volume in the final state, this process is allowed by the second law. One example suffices to illustrate the point. If an ideal gas is expanded reversibly and isothermally, work is done by the gas. Since delta U equals 0, the work done is equal to the heat absorbed by the gas during the expansion. Hence, a certain quantity of heat is converted entirely into work. This is not the sole effect of the transformation, however, because the gas occupies a larger volume in the final state. This process is allowed by second law. The Kelvin statement K and the Celsius statement, Clausius statement C, are equivalent. To prove this, we prove that if the Kelvin state is false, the Clausius statement is false, and vice versa. The proof that if K false, C false, suppose K is false. Let me see how much we put it. Let me stop around here. First, define an engine to be a thermodynamic system that can undergo a cyclic transformation. That is a transformation whose final state is identical with the initial state. In which system does the following things and only the following things. In which system does the following things and only the following things. Absorbs the amount of heat which is larger than 0 from reservoir T2. Reject an amount of heat Q1 which is larger than 0 to reservoir T1 with T1 smaller than T2. Performs an amount of work W is larger than 0. Suppose Clausius statement is false. Extract Q1 from reservoir T1 and deliver it to reservoir T2. It's complicated. Okay, so there is a T2, T1. Yeah. So we absorb. This is like Q2, and we are reject Q1. Then we perform work W. Suppose we reject Clausius statement false. Extract Q2 from reservoir T1 and deliver it to reservoir T2 with T larger than T1. Operate an engine between T2 and T1 for one cycle and arrange the engine so that the amount of heat is extracted by engine from T2 is exactly Q2. The net result is that an amount of heat is extracted from T1 and entirely converted work into work. So no other effect. Hence, K is false. It's kind of difficult. Let me see where. I skipped this one. Proof that K false, C false. Suppose K is false, then we can extract heat from reservoir at temperature T1 and convert it entirely into work with no other effect. Now we can convert this work into heat and deliver it to a reservoir at temperature T larger than T1 with no other effect. A practical way of carrying out this particular step is illustrated by Joule's experiment on the equivalence of heat and energy. The net result of this two-step process is the transfer of amount of heat from a colder reservoir to a hotter one with no other effect. Hence, C is false. Proof that C false, K false. First, define an engine to be a thermodynamic system that can undergo cyclic transformation, in which the system does the following things, and only the following things: absorbs amount of heat Q, which is larger 0 from reservoir T2, reject amount of heat Q1 to reservoir T1 with T1 smaller than T2, performs amount of work omega equal larger than 0. Suppose C is false. Clausius' statement is false. That means you cannot transfer heat from cold reservoir to hotter reservoir. Suppose C is false. That means you can deliver heat from cold reservoir to hotter reservoir. Extract Q2 from reservoir T1 and deliver it to the reservoir T2 with Q2 T1 larger than T1, T2 larger than T1. Operate the engine between T2 and T1 for one cycle and arrange the engine so that amount of heat extracted by the engine from T2 is exactly Q2. The net result is that an amount of heat is extracted from T1 and entirely converted into work with no other effect. Hence, K is false. Let's change extract Q. Okay, then we put Q1 up. Okay, so maybe I stop today here, which is page